Hey, welcome back, you crazy cats. Today we're talking about heat and heat transfer. Heat is a form of energy and therefore is measured in joules. There are other units of heat, though the most common one is the kilocalorie. 1 kilocalorie is defined as the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius from 14 degrees Fahrenheit, or 14 degrees Celsius to 15.5 degrees Celsius. I think that's should be, I don't know if I said 14.5 degrees Celsius. 1 calorie is 0.001 kilocalories. Confusingly, the calories listed on nutrition labels in the U.S. are really kilocalories, sometimes called calories. Some other labels are more accurate. Left, which is Australia, right, which is Germany, you'll see that they're a whole lot more accurate. They talk about in Australia's low joule cola. They're talking about joules as the amount of energy. Here in Germany, they talk about 1 kilocalorie, all right, and that's 0.3 liters. Okay, here are the three most common units of heat. And if we look over here on the left, they show us that 1 kilocalorie, or 1 capital C calorie, is the amount of heat needed to raise 1 kilogram of water 1 degree Celsius. So if you put 1 kilocalorie or capital C calorie of energy into 1 kilogram of water, it's going to raise its temperature by 1 degree Celsius. Now let's look at 1 gram of water. It would only take 1 calorie, small c calorie, of energy to raise 1 gram of water 1 degree Celsius. And then ones we hear about all the time, if you ever listen to what's happening with air conditioners or furnaces, is the British thermal units, or BTUs. And this makes reference to 1 pound of water. If you were to put 1 BTU of energy into 1 pound of water, it would raise it 1 degree Fahrenheit. So, if heat is energy, how do kilocalories convert to joules? Careful experimentation using the apparatus below gives the answer, as the work done by the following weights raises the temperature of the water. So as the weights here would fall, it would turn these paddles down here, getting the water to move faster, creating heat. This relationship is called the mechanical equivalent of heat. 1 kilocalorie is equal to 4,186 joules. Let's talk heat transfer. There are 3 types of heat transfer: conduction, convection, and radiation. Conduction is the transfer of heat through a substance, such as a disposable cup that holds your hot coffee. If the cup is a good conductor of heat, you will need a sleeve to keep from burning your hand. Typically, metals are good conductors of heat. They have electrons that are free to move throughout the material, and non-metals are not. Non-conductors of heat are also called insulators. The heat flow rate through a slab of material is proportional to its surface area, and the temperature difference is inversely proportional to its thickness. The constant K is called the thermal conductivity. So, as we look here, all right, the change in energy over the change in time, and energy over time. So what we're really talking here is power, work over time, energy over time, is equal to its thermal conductivity times the area times the change in temperature over its thickness. This diagram illustrates the geometry of heat transfer by conduction. So here's our equation. We were down here. Let's look at this here. The amount of energy over time, or the amount of power, but energy, change in energy over the change in time that's going into this, is going to be equal to, first of all, how well does it take on heat, times the surface area that it's the heat is flowing into, times the change in temperature. All right, they're telling you here the change in temperature from one side to the other. How well is it letting heat flow through it? On one side it's got a certain temperature, on the other side it's got a lower temperature, and divided by the thickness. On here, this is an example of lots of thermal conductivities, the K, of several materials that we'll use from time to time. You don't have to write these all down, but make sure you know where this is, because in your homework you're going to need it from time to time. When insulating a house, we want materials whose thermal conductivity is as low as possible. So as you see here, the pink stuff, there's our thickness. Here's another thickness of another material. They're telling us that the temperature 1 is 20 degrees Celsius, the temperature 2 is 8 degrees Celsius. What we're going to find out here is that the heat flow is going to have to go through the wood, through the pink stuff, to get to the outside. It's going to go from hot to cold. All right, temperature 1 was 20 degrees Celsius, temperature 2 was 8 degrees Celsius, so it's moving in a direction from hot to cold. Okay, heat transfers in fluids mostly by convection, which is the result of mass transfer. That is, heat is transferred as warmer fluids move to replace cooler fluid. Convection may be spontaneous as below or forced. So what we see here is they're showing convection. During the day, the land gets hotter than the water. So as the hot air rises, right, over the ocean we have this cool air. So the hot's going to move towards the cool, and then the cold air is going to be coming up here. So during the day, if you were standing right here on the beach, that's why you feel the cool breeze coming towards you. If you were to be standing out here at night, right, it's at night, the land is going to cool off faster, so that cool air is going to go down. The ocean is going to be hot, or not necessarily hot, but much warmer, so the air is going to go up, and what you get then is this convection as the air transfers. So you would feel, if you're looking out at the ocean, you would feel the air to your back, or the breeze to your back. The same thing works in your house. It's how your furnace works. Your furnace heats the air up, the hot air. Now it's forced, but it would naturally, if they didn't force it, it would still naturally go up. You have a hot air register. You have the air that comes up. As it goes up, it loses some of its energy. As it begins to lose energy, it gets cold, and it comes back down. That's why cold air registers are typically on the floor, or they're on the bottom. Now, that's not true in all houses, but that's where you typically find the cold air registers, or the cold air return. They're at the bottom because the air at the bottom of your room is colder than the air at the top. Heat transfer. Radiation is the only type of heat transfer that can take place through a vacuum. You can feel the radiation of heat when you stand near a fireplace. This radiation is in the form of electromagnetic waves in the infrared part of the spectrum. The sun. All right, we got the sun and we got Earth over here. Earth and the sun, and this big void. All right, meaning there's this vacuum. There's nothing between the Earth and the sun. There's no mass, no matter. There's this vacuum. So the sun transmits energy or heat to the Earth through this vacuum by radiation. All right. The sun does not transfer energy by conduction or by convection to the Earth, because both those types of transfer require a material or a medium. Radiation is the only one that does not require a medium. Heat transfer. All right, so the rate of energy radiation is given by Stefan's law. Notice that we said earlier that the change of energy, or the change of time, or power, all right, which is equal to power, is going to be equal to, this right here is what we refer to as Stefan's constant, times the area, times E, which is the emissivity, and the temperature change to the fourth power. All right. Stefan Boltzmann constant. Sorry, that's the Stefan Boltzmann constant. We'll do some work with this in class. A good emitter of radiation is also called a good absorber. I guess we're going to go with that. I'm not sure what else I'm supposed to say about that. Okay, here we see the three types of heat transfer. In this case, the fire is putting off radiation, so you can feel it from a distance. On here, there's convection because if you put your hands above it, the heat is going up. All right? And if you put a metal rod in the fire, the tip is going to get hot, and it will slowly start to maybe bend, is what they're saying here. But conduction, the heat will start to transfer up the rod and possibly up to your hand by conduction, because all of these particles in here are touching each other. A thermos bottle minimizes all three types of heat transfer. A good thermos bottle. In a thermos, they're going to have an inner wall, and that's going to be made out of glass. And they're going to have another wall, typically made out of glass. So what you have in here, this white area, is what we call a partial vacuum. This vacuum means that there's no medium. So what do you think they're trying to protect against there? Radiation. All right, there's no heat loss or heat gain due to radiation because of the vacuum. Hot or liquid cold, that would be in here. They also typically have a silver film in here. The reason they have that silver film is they're trying to protect against radiation. It's going to allow the rays to the rays that are coming in are going to be reflected out. Anything that's in there is going to be reflected in. It's going to stay in there. It's not going to be able to leave the heat that's in there. A lot of times then also they're going to have the outer wall here. A really good one is going to be something that doesn't allow conduction to happen because they don't want heat to transfer in because of conduction. And then convection, if you put a lid on it, heat can't go out as well. Heat transfer, all right? Passive solar heating uses the changing angle of the sun to warm buildings in the winter, but not in the summer. So as you can see here, during the summer, all right, the sun is coming down at a much steeper angle. So the sun isn't able to get into the house or into the building. Winter solstice, we'll go the other way now. The winter is the sun is coming at a much smaller angle. And you're able to get much more sun rays into the house or the building to warm it up. More on heat. Radiation. Transfer of heat through straight lines. So remember that radiation is going to be coming from the sun. Could be coming from a lot more than just sun, I guess. I was thinking sun there. But it could be coming from fire. But it's going to be coming through straight lines. And these lines are from the electromagnetic spectrum. Very specifically from the infrared part of the electromagnetic spectrum. Colors and heat. Last things we need to talk about. Blacks are going to absorb all light, thus warms fast and cools fast. Black, again, is going to, because it absorbs all the colors of the light, it's going to be absorbing more energy because it's not reflecting any energy. White, it reflects all light, so it doesn't absorb any electromagnetic energy. Parts of the electromagnetic spectrum. It reflects all light, so it's going to be not absorbing any of the energy, it's going to be reflecting, so that's why white is much cooler. Well, hey, that was a whole lot of information today. I'm sure that was informational. I'll catch you guys on the flip side.